In this video, we'll review how to solve first-order differential equations with sinusoidal inputs using complex replacement and the exponential response formula. In Part A, we will use complex techniques to solve x dot plus kx equals cosine omega t, where k and omega are constants. Cosine omega t is the input in this equation, and x is the response, which we want to find. In Part B, we will use our work from Part A to solve x dot plus kx equals f sine omega t, where f is a constant. Notice that the two left-hand sides are the same, but the inputs are different. In Part C, we will use the superposition principle to solve, again, the same left-hand side, x dot plus kx, but our input is now cosine omega t plus 3 sine omega t. Finally, in Part D, we will use our work from Part A again to solve x dot plus kx on the left-hand side again, but our input is cosine omega t minus phi, where phi is a constant phase shift. Take a moment to pause this video and try these problems on your own, and we'll be back in a moment. Welcome back. For this problem, for each part, the general solution, x, is equal to the solution to the associated homogeneous problem plus a particular solution. In this video, we will only be finding the particular solution for each ODE, but it's still important to find x of h, so you should do this on your own as an exercise. For Part A, our ODE is x dot plus kx equals cosine omega t. Okay, and to solve this, we're going to use complex replacement. By realizing that cosine of omega t is equal to the real part of e to the I omega t. So we can complexify this ODE by writing z dot plus kz equals e to the I omega t, and we'll find a particular solution to this ODE. Once we do that, we take the real part of that solution, which will give us a particular solution for our original ODE. So x sub p will be equal to the real part of z sub p, where this is a particular solution for this ODE. Okay, so to solve the ODE for z, we're going to use the ERF. We'll need the characteristic polynomial, which is p of s equals s plus k. And the ERF tells us that a particular solution, z sub p, is equal to 1 over the characteristic polynomial evaluated at I times the frequency times the right-hand side, e to the I omega t. Substituting I omega into the characteristic polynomial gives us 1 over k plus I omega times e to the I omega t. Okay, now we're going to decompose z into its real and imaginary parts. So we're going to rationalize the denominator. So we're going to multiply the numerator and denominator by the complex conjugate of the denominator. That will give us k minus I omega over k squared plus omega squared times e to the I omega t. And we also want to write this as a sum of sines and cosines using Euler's formula. So we get k minus I omega over k squared plus omega squared times cosine of omega t plus I sine omega t. Okay. Now we just need to take the real part of the solution to get x sub p, our particular solution. So x sub p equals the real part of z sub p, which is equal to 1 over k squared plus omega squared times k times cosine omega t gives us a real a real part, so this is cosine omega t. And then minus I omega times I gives us a plus omega times sine of omega t. So this is our particular solution to the ODE in part A. So now that we've found this, I'll let you work through the problem in part B, and we'll be right back. Welcome back. Now before we start part B, I just want to point out, did you notice that z sub p was written in rectangular form? We could have also written it in polar form, but for this video, we just made the choice to use rectangular form. So let's start with part B. And our ODE in this case is x dot plus kx equals f times sine of omega t. Okay? So if we use complex replacement again, we notice that f sine of omega t is equal to f times the imaginary part of e to the I omega t. Okay? So the complexified ODE is z dot plus kz equals f times e to the I omega t. But we already solved this problem. This ODE for z is the same as this ODE, except that we're just multiplying the right-hand side by the constant f. And by linearity, this f would just carry through all of our calculations. So we can write down our particular solution, z sub p, by just writing down our particular solution from part A multiplied by the constant f. So now we have f times k minus I omega over k squared plus omega squared times cosine of omega t plus I sine of omega t. And again, x sub p is now in this case it's the imaginary part of z sub p. So to get the imaginary part, we have f over k squared plus omega squared. And now we want the factors that are multiplied by I. So minus I omega times cosine omega t means that this will give us a part of the imaginary part. So we'll get a minus omega cosine of omega t. And k times I sine omega t is also part of the imaginary part of zp. So plus k sine of omega t. So now this is our particular solution for part B. And since now we've completed part B, I will let you work through part C, and we'll come back in a moment. I've just erased the boards, and let's recap what we did in parts A and B. In part A, we used complex replacement and the exponential response formula to solve x dot plus kx equals our input cosine omega t. And we found a particular solution, which I've rewritten here, but I've relabeled it as x sub a, just so remember that this particular solution corresponds to part A. In part B, we used complex replacement as well as our work from part A to solve x dot plus kx equals an input of f times sine omega t. And we found this particular solution, which again I've relabeled as x sub b so that we remember which part this corresponds to. Also remember that part A was found by taking the real part of the particular solution to the complexified ODE, and part B was found by taking the imaginary part of that solution and multiplying by a constant f. So now we're going to move on to part C, which is to solve x dot plus kx equals cosine of omega t plus 3 sine omega t. So to solve this, we're going to use the superposition principle. We saw in part A that this particular solution satisfied the equation x sub a dot plus k times x sub a equals cosine of omega t. This particular solution for part B solves the equation x sub b dot plus k times x sub b is equal to, if we let f equal 3 in this case, we can write 3 sine of omega t, where f equals 3. Okay? So now, by linearity, we can write that d dt of x sub a plus x sub b plus k times x sub a plus x sub b is equal to the sum of the right-hand sides. Cosine omega t plus 3 sine omega t. And now, the superposition principle tells us that since xa plus xb here is just x in this equation, we can write down the solution to this equation by simply taking the sum of the solutions from part A and part B. So we get that x sub p for this equation is equal to 1 over k squared plus omega squared times our factor from part A, which is k cosine omega t plus omega sine of omega t, plus our factors from part B, which are, we're letting f equal 3 here again, so remember that this will be minus 3 omega cosine omega t plus 3k times sine of omega t. And we can combine like terms in this expression to get that x sub p is equal to 1 over k squared plus omega squared times k minus 3 omega times cosine of omega t plus omega plus 3k sine of omega t. Okay, so this is the particular solution to the differential equation in part C. And notice that, again, it's a linear combination of cosines and sines. So now we're going to move on to part D, and I'll let you work on that before I come back and we go through it together. Now let's move on to part D. In part D, we're solving x dot plus kx equals cosine omega t minus phi. Now, this might look a little bit complicated or confusing, but there's a shortcut on how to solve this. If we notice that we can rewrite this as x dot plus kx equals cosine of omega times t minus phi omega, so I've just factored out an omega here, we can actually use what's called time invariance. That's because this is a linear ODE, and none of the coefficients depend on time, so we can apply this concept. Now, this ODE might look familiar now, because in part A, the ODE that we solved was x dot plus kx equals cosine omega t. Now, the only difference is that the t in this case is replaced by t minus phi over omega. So this is just a shifted time. Time invariance tells us that the solution to this equation, which has an input that's shifted in time, is the same as the solution to this equation with that same time shift. So if we look back at our solution from part A, our solution for part D will be the same, except that instead of t, we'll write t minus phi over omega. So let's write that here. So x sub p for part D is going to be equal to 1 over k squared plus omega squared times k cosine of omega t minus phi. So when I substitute this in for t, omega distributes through, and I get this factor again, plus omega sine omega t minus phi. And that's the solution for the ODE in part D. Now we could have gone through and done the ERF and everything all over again, and we'd get the same answer. But this is just a nice property of the equation that we could just apply the work we had done previously.